Okay, we begin. 10:10. Welcome to the first session of the CHES number 25. Yes, it's 25. Okay, so the first talk will be given by Émeric Genet about on protecting Sphinx plus against false attack. Okay.
Okay. Thanks for the introduction. So my name is Émeric, and this is my paper on protecting Sphinx Plus against fraud attacks. So to give you a bit of context, so quantum computers will destroy RSA and ECC. This is due to a famous result of Shor's algorithm, which offers a super polynomial boost in solving both the factoring and the discrete logarithm problems. So as a result, this incited NIST to come up with substitutes that are resistant to quantum computing. And they basically held a post-quantum standardization project during the past years. And last year, a few winners were selected for standardization, and among which there is Sphinx Plus, which is a stateless hash-based digital signature algorithm, which is the topic of today's talk. So industrialization of these standards will require secure implementations. So in particular, implementations that are resistant against side channel and fault attack. And in particular, in 2018, there was this devastating fault attack against all Sphinx variants, which we're going to see today. And the sad thing is that there was no defense against this attack to this day. And so I spent most of my time as a PhD student to come up with a solution, and I failed. So here is how. So here is today's menu. So first, I'm going to show a very quick introduction to Sphinx Plus. Then we're going to see the fault attack in question. And finally, we're going to analyze the caching countermeasure in the context of Sphinx Plus. So let's first discuss Sphinx Plus. So if you joined this talk in hope that you were going to have a full description of Sphinx Plus, I have bad news for you. This is absolutely impossible to do in the time allocated for my talk. So instead, I'm basically just going to assume that you all know what Sphinx Plus is, and I'm just going to show a very broad overview of the thing. So basically, Sphinx Plus is a combination of many things. So there is what we call one-time signature, which are laid out in multiple layers, as you can see on the slide. And these one-time signatures are just combined 2 by 2 to create what we call hash trees with a hash function. And this obtains what we call multiple time signature scheme, which is a scheme that you can use up to a certain number of times. There's also a layer of few time signature, which I'm not going to enter into the details because we don't have time for that, but it's not that important for the purpose of this talk. The public key is just basically the root of the topmost tree, while the signing key is just a secret seed that is used to generate all the key pair across the tree structure. The key feature of Sphinx Plus is that this is a stateless scheme, which means that it can act as a drop-in replacement for any deployed signature scheme that is currently used. And this is achieved by pseudo-randomly generating a path in the tree to sign the message. So what I mean by that is that suppose that you want to sign a message. So there is a value R that will dictate the path that the message will take in the tree up to the top. And basically, the message is recursively signed by all the instances of one-time signature that it can encounters on the path from the bottom to the top. And as a result, a signature will just be like all the signatures of the instances it encountered, along with all the nodes in the trees that would allow a verifier to reconstruct the root and then compare it to the public key. Okay, so sorry, it was a bit fast, but that's basically Sphinx Plus. Still, we're going to see the WRTS to maybe give you a better grasp at how hash-based digital signature work concretely. So WRTS stands for Winton-is one-time signature. It basically consists of a hash chain of intermediate values. So the value on the left is secret, while the value on the right is public. So it's like the public key. And how does it work? So suppose that you want to send a message of 2 bits, say 0 and 1. What you're going to do is that you're going to reveal the intermediate value that corresponds to the value of the message, so 0, 1. So here the signature would be x01. There is an obvious problem with this approach. By knowing x01, you also know x10, x11, because the hash functions are public. So how do you prevent this? Well, what you're going to do is that you're going to draw a second chain that works exactly the same as the first one, but you're going to use it to sign the bitwise inverse of your message. So if your message is 0, 1, as in this case, then your bitwise inverse is going to be 1, 0, and you're going to reveal C10 as part of your signature in addition to X10. So now if you want to use the X10 and X11 to forge a signature for these messages, you would need these values as well, which are hidden at least behind one hash function. So as the name indicates, this is a one-time signature, so you should be using this only once. And that's it for how the WOTS scheme works. All right. So now that we've seen how Sphinx Plus works, let's see how we can attack it using a fault attack. So for the scope of this presentation, a fault attack is basically going to be a corruption of data during the signing procedure. So the fault model is quite simple. So we assume that a fault can happen anywhere during the signing procedure, and that it hits only hash functions. So why can we assume that? Well, because this is a hash-based signature, so it will spend most of its time hashing things anyway. Moreover, we're going to assume that a corruption is one to many bit flips of any register in the signing process. And the key feature is that with this fault model in mind, we will have random value, like uniform random value at some point in our scheme. So why is that? We have like a simplified sponge function on the screen. And due to the avalanche effect of hash functions, which is a desirable property of hash functions, a single bit flip will eventually output completely uniform bits at the end. All right, so with that in mind, let's see how it applies to Sphinx Plus. So remember, in Sphinx Plus, we have hash trees, which basically consists of compressions of public keys of WOTS. So I insist on that. It's public keys that are being compressed, and it does not depend on any message. So these trees in particular are just the same from one execution to another. So that's why they can be signed with a one-time signature. Problem is, what happens if there is a fault? Then you will have the root of the tree, which are going to completely deviate from its intended value, and that is going to be blindly signed by the next WOTS in line. So then you will have a second signature that is different from the valid one. And by knowing the valid one, you will have two signatures for one time one-time key pair. So here is how it looks. So remember the hash chains in WOTS. Normally you should have this, but with a fault, then you will have a different message that enters the instance, and the signature will just be different values in the chains. And by combining these two values together, you will be able to forge a signature for a variety of messages, even the messages for which you didn't get the signature. Okay, in the context of a Sphinx Plus signature, a faulty WOTS signature can have two effects. So the first thing that can happen is that the signature, even though it's faulty, can still be what we call verifiable. So a verifiable signature is just a signature for which the verification procedure returns true when you use it with the appropriate message. So how can that happen? Well, if the fault occurs in the derivation of the authentication nodes that are provided in the signature, then the verifier can just recompute the faulty root, and the faulty signature will correspond to this root. So nothing funny is happening here. You will just have a valid signature even though it was faulty. So how then can it be non-verifiable? Well, if the provided nodes are the same, but a fault occurs in the path from the WOTS to the root, then the root is unknown to the verifier. The verifier will just recompute an intended value, and the faulty signature will not correspond to this value. So then the verification will just return false. All right. The second thing that can happen is that the fault can be exploitable. So what we mean by that is that it's only a faulty signature that features a faulty WTS, and it happens only if the fault occurs not on the top layer, because on the top layer there is no WTS involved. All right. So how often do you have these kinds of signatures? Well, actually, it turns out that it's extremely likely to get both an exploitable and a verifiable signature across all instances of Sphinx Plus. So this is kind of critical because remember, we don't have absolutely any control over our fault. It's just one random bit flip that occurs anywhere in the whole thing. So the two main takeaways of this number is that a random fault is extremely likely to be exploitable. So it means that you need to take fault attacks against Sphinx Plus very seriously if you plan to deploy Sphinx Plus. And the second takeaway is that verifying doesn't work. You can't detect faulty signatures by just verifying the output of your signing process. All right. So now that we've seen what can happen, so how can an adversary exploit the faulty signature to forge a valid signature for another message? So actually, the adversary can mount a universal forgery. So the first step is to basically collect signatures and make sure that you have like at least 140 signatures in your signature collection. So remember, you need 2 sigmas for this to happen. So you either need like 140 signatures and the valid one, or just 2 faulty signatures, which works as well. So now that the adversary has collected many signatures for at least one keeper, the goal is to basically to graft a subtree. So the adversary achieves this by figuratively cutting a tree at the WTS that is compromised, and then basically come up with another subtree for which the signature can be forged using the faulty signatures and the valid signature. All right. The next step is to basically forge the bottom part for any message. So since the subtree is controlled by the adversary, they can use it to forge any signature. Additionally, the adversary requires to find a value R such that the path that the message will take goes through the compromised WTS. And finally, the adversary will just extract a valid top part from a Sphinx Plus signature and patch it together with the rest. And in the end, that's what you get. You will be able to forge a valid signature for a message of your choice. And this is quite critical. Like, words cannot describe how bad this attack is against Sphinx Plus. So that's why I came up with numbers instead. So basically, the main takeaway of this slide is to show you that all these numbers are within reach. So even though you have only one reuse of one WTS somewhere in the scheme, you are able to do the universal forgery with relatively easy complexity. So I say that because you may have a look at the path-seeking complexity, for instance, and say, hey, this is quite high. But just realize that the path-seeking step in the universal forgery is just a proof of work. For instance, the 2 to the 64 is just basically Bitcoin's proof of work. So wouldn't be a shame if people like build clusters of machines just to solve this particular problem because they had some kind of money incentive to do so. So yeah, all these numbers are within reach. And as a result, it's quite hard to prevent the universal forgery to happen if you manage to get 40 signatures and a valid one for a same keeper. So if you remember the topic of today's talk, I was supposed to show a countermeasure against this. And this is basically why I drew this table. I basically wanted to identify one step in the universal forgery to make it hard. And actually, I realized that there was no way to make it super hard. So the best bet is basically to prevent a 40 signature from being output. And this is why we're going to analyze what we call the caching countermeasures. So the idea of the caching countermeasures is really simple. So you will store the WRTS that you compute in a cache, and then every time that you require the signature upon further request, you will just look up the results and link it to whoever needs it. So if there are computer scientists in the room, you may know this process as dynamic programming. But yeah, for engineers, caching is going to be more understandable. So you have two strategies for caching WRTS. So either you cache all the WRTS on the layers. Otherwise, you can cache all the WRTS in a path from the bottom to the top. And let's consider first caching layers. So how effective is caching layers against the fault attack? Well, if you look at the probability of getting an exploitable fault with the same fault model as before, you will see that the probability does diminish with the number of layers that you cached. But the problem is that it gets pretty expensive very quickly. So for reference, I put like the required memory that you would need to deploy this countermeasure. And yeah, it gets super expensive if you really want to like defend yourself against the fault attack. And even so, suppose that you're completely out of your mind and you're willing to spend like $11,000 just to cache one-time signatures. Well, you just go from 93% to 77%. So it's underwhelming, to say the least. All right, let's now consider caching branches. So if I were to draw the same table on the fault exploitability, we would get pretty much the same result. But there was one problem that I wanted to share with you, which was interesting to me. So it's how many queries on average do you need to trigger a recomputation when the cache is dynamic? So now we have a dynamic cache. Some signature will enter the cache, and you have a cache capacity of C out of N, and you basically want to know how many queries do you need to trigger a recomputation, this time maybe with a fault. So you can represent this with a Markov chain. So the state in the Markov chain just basically represents the number of unique signatures that enters the cache until recomputation. So since the cache is dynamic, well, it starts empty, then it builds up. So the loop arrows are like cache hits and the straight arrows are cache misses. And until the first cache eviction happens, and then it means that there is at least one signature that is available for recomputation. And with a bit of chance, you will get a WRTS that is recomputed, and this time maybe with a fault, so you can attack the scheme. You basically solve that as a stochastic process. I'm not going to enter the detail, but if you plug in the numbers from the Sphinx plus parameter set, you will get these results. And again, this is quite underwhelming. So if these numbers were like super high, you would say, hey, okay, but still, it's hard for the attacker to retrigger a computation, so it should be fine. But here, even if you consider like the last column, it's like everything is cached but one signature, and you can see that it's not that much complex for the attacker to retrigger recomputation. All right, so that was my talk. So the main takeaway is that Sphinx Plus is extremely fragile against faults. So if you plan to deploy Sphinx Plus, you need to consider faults in your threat model, even though you are in an environment where you believe that no faults will occur. So caching is not effective. So for now, until someone smarter than me take on the problem, I would suggest you to recompute at least 2 times your signatures. Before someone asks me, yes, the attack applies to whatever Sphinx variants that you can think of. And this is because we're not exploiting a bug in Sphinx Plus, okay? We're basically just exploiting the design of the scheme itself. As long as one-time signature will be reused to be recomputed for a single message, you will have this attack that applies on the scheme. So yeah, check out the paper for more. So I did an extensive analysis of Sphinx Plus in presence of faults. I also have public repository with attack scripts, formulas, and also experiments. And that's it. Thanks for your attention.
Okay, thank you very much. nearly 30 seconds left. So time for questions. No?
Thank you for your talk. Maybe a drastic countermeasure. What would happen if you would replace the Internet's one-time signatures with a few-time signature scheme? Because I think in that case, well, you don't have the problem with re-computing a signature in the tree.
Yes, so the question was, what if you replace WTS with few-time signatures? So if there is an accidental reuse, then you should be fine. And the answer is yes, you can do that. The problem is that the few-time signatures are very, very big compared to WTS. So I don't know if you remember the slides, but basically the fourth layer, which is like at the bottom of the tree, it consists of like 60% of the computations of Sphinx. Even though it's just one layer, it's very, very big. So you can do that, but then it will really suffers from a big performance problem.
Thanks.
Okay, other questions? Okay, nothing on the chat. So, okay, thank you very much. And we wait 4 minutes for the next talk. Okay, thank you.
Thank you.
Mm-hmm.
Okay, finally we begin. So it's a talk given by Sanders Zuri, sorry, and the co-author Vincent Yulish, Alexis Bagia, Mehdi Tibucci, and Jean-Pierre Seifert. It's about loop abort strike back, defeating fraud countermeasures in lattice signature with ELP. And let's go.
Thank you. How can I move?
Please.
Okay.
So my name is Sundes, and I'm going to present today our research paper entitled Loop Abort Strike Back, Defeating Fault Countermeasures in Lattice Signature with Integer Linear Programming. So this work was a cooperation between Technical University of Berlin, ST Microelectronics, Entity Labs, and Fraunhofer SIT. And I have here in the first row my one of my co-authors, Alexis. So today in the presentation, I will start with first an introduction, Then I will explain or I will give a high overview of the Dilithium scheme, and we will go together through the recent attacks and the countermeasures to explain our attack, because it's in fact, it builds on the proposed countermeasures in the literature. Then in section number 5 and 6, I will go through the experimental setup of our implementation, and also I will present a simulation or the result of the simulation of our attack, because we also took into account that it could be that the attacker doesn't have exactly the same lab conditions as ours. And I will conclude with section number 7. So as we all know, the National Institute of Standards and Technology announced 3 post-quantum signature candidates. One of them is Dilithium, and Dilithium is known as good algorithm from the point of view performance. And as it is going to be standardized, it is going to be implemented in embedded devices. That's why the security against side channel attacks and fault injection attacks is really a desirable property by the National Institute of Standards and Technology. So that's why we are interested in seeing or investigating the security of Dilithium against side channel attacks or fault injection attacks, and to which extent the current implementation, taking into account, of course, the countermeasures suggested previously, to which extent this is going to be considered as a secure scheme. So Dilithium is a post-quantum signature scheme which belongs to the lattice cryptography family, and it builds on Fiat-Shamir with abort paradigm. It relies on modular lattices, which means our operation will be on matrices and vectors of polynomial over a ring RQ, and the security of the scheme is based on 2 lattice problems: the learning with error, or the modular learning with error, and the shortest integer solution problem. Interestingly, there are 2 versions, the deterministic one and the non-deterministic one, and the non-deterministic version of Dilithium is expected to give more security against fault injection attacks. So to understand the attack of today, it is important to have an idea about how Fiat-Shamir with abort works. So as we see here, Fiat-Shamir with abort can be seen as a zero knowledge protocol where we have the commitment and the challenge happening on the same side, the signing or the signer side. First of all, we will need a secret key, which is sampled from a restricted domain. And here I mean by L, we have L polynomials as we are working in modular lattices. And we will need the verification key, of course, which is the hash of the secret. To sign a message M, we will have first to construct our commitment vector, sampled from a restricted domain as well. And after that, we have to construct the challenge, which is the hash of the message and the commitment vector. And after that, we construct the preliminary, let's say, signature, SC, plus the commitment vector. And it's also sometimes called the masked vector because it masks the information on the secret. Now, this is a preliminary signature because we have always to check whether the Z reveals some information on the secret key. That's why we do a rejection, and that's why the name is Fiat-Shamir with abort. Then if we want to do the verification, we have to go through 2 steps. First, we have to check that our Z is in a certain interval, and then we have to calculate the C. And if you just do the calculation, you will end up with the same results as in line number 2 because the hash is homomorphic. So if you notice here, the signature are relying on a commitment or on the sampling of a commitment vector. And in the literature, there were 2 ways of sampling this vector. The first was the discrete Gaussian sampling, which was considered as non-secure from the point of view side channel analysis. And that's why in Dilithium, the designer, they made a deliberate choice to pick uniform sampling for the commitment vector in order to make the scheme more secure against the side channel attacks targeting the discrete Gaussian sampling. So now let's see how this Fiat-Shamir applies to Dilithium. This is a simplified version of Dilithium, but it will be enough to understand the attack of today. So one thing is the Dilithium scheme has a secret key, which is separated in 2 parts. S1 and S2. And then when the scheme was designed, it was seen, or it was, the designers were sure that if you have S1, you will not be able to generate a valid signature. But then afterwards in the literature, there were two attacks where they show that if you have only S1, you will be able to generate a legitimate signature. And that's why in this attack today, and also in some attacks in the literature, if you get S1, we consider it as the equivalent key, because you will be able to generate a legitimate signature. Then the signing happens in this way. So you have exactly the same structure of the Fiat-Shamir with abort. You sample your commitment vector from a restricted interval gamma 1 minus 1 gamma 1. You have L polynomials, and then the challenge vector should be constructed. And here one property that we will need afterwards to understand the attack is that the challenge vector is one polynomial of 256 degree for all the NIST security level. And exactly tau elements of this vector are going to be set to non-zero, and they will be whether -1 or 1. And the rest, of course, are going to be zero coefficients. And then we construct the signature Z equal to Y plus CS1, and then we have the rejection condition that we are not really interested in that because we don't need it for the understanding of the attack of today. So as you see here, from an attacker point of view, if you have the Y or the commitment vector, it will be easy to get the S1 somehow. And that applies also to all Fiat-Shamir with abort schemes. That's why most of the attacks in the literature on Fiat-Shamir and also on Dilithium, they target the commitment vector, whether with timing attacks, for example, or with side channel analysis. So there are attacks on both versions, like the discrete Gaussian sampling and also the Dilithium. There was a paper last year at the SLC. And today we are interested in fault injection attacks. So how can we get the secret key of Dilithium through a fault injection attack? In the literature, there is only one paper talking about this. And it is actually an attack or a fault, loop abort fault on lattice-based schemes relying on Fiat-Shamir with abort and hash and sign. Let's first understand this, because our attack will build on the countermeasure of this paper. So this paper, as I said, it applies to all Fiat-Shamir with abort schemes, but now we will see how it works on Dilithium. So first of all, the attacker will inject a fault during the sampling of the commitment vector, and then we will have our faulted signature, as you see in line number 6. So the idea of the attacker is they will rewrite the signature in the following form. And we have here that the index M is the first, or the index of the first faulted coefficient. That means from 0 to M-1, you will have your normal, or let's say non-faulted coefficients. And then starting from the index M, you will have 0 coefficients. And then to get the secret key, the authors, they try to solve a lattice problem and calculate the secret key. But one very important constraint here is that they have, or the attacker should know in which index they faulted the signature, which means the M is really important here. Otherwise, we'll not be able to get the secret key based on this attack. And this constraint was used to design countermeasures. So the authors came with two ways to make it or make Dilithium more secure. The first one is that you do a shuffling so that the attacker will not be able to know which coefficient is equal to 0. Or you perform a rejection sampling to ensure that your polynomials are not of low degree. If we want to apply this countermeasure on Dilithium, so I present here a pseudocode of the sampling function in Dilithium, which is basically we have a loop over all the polynomials and then over all the coefficients of each polynomial, and the convert path function, it converts the random bytes into a coefficient or an integer in a certain range. So if we would like to implement the shuffling or this countermeasure to make the scheme more secure against the current attack, then we will have to do a shuffling of the Y coefficients, as you see here in line number 7. So today I'm going to explain, or I will present our attack, which basically built on this countermeasure, and we will prove that even if we don't know where are the zeroed coefficients, we still can solve the equations and get the secret key S1. So our attack, it bypasses the shuffling countermeasure. The countermeasure also of rejecting low degree polynomials. It can work with very little faulted coefficients, of course, at the expense of more signatures, faulted signatures. And it can break the deterministic as well as the non-deterministic version. And it can also extend to the case where we know the value or the coefficient, because they will be set to some fixed known constants. How it works in 3 steps. So first of all, let's make sure that the attack is going to be mounted on a shuffled version of Dilithium. So first of all, we inject our fault in the same way as in the literature, no any changes. We target the sampling function. And after that, we will come up with some condition in order to filter out the equations for which the y coefficients are non-zero. And after that, we will search for the secret key by maximizing the fulfilled equations in our integer linear program. So let's start now with the first step. So this is the shuffled sampling function in Dilithium. As you see, we have the shuffling in line number 7. We will introduce the clock glitch, and then we will set some coefficients of the y polynomial to 0. After that, we shuffle, and it's worth mentioning here that when we shuffle, we wanted to make the attack or the more difficult, so we shuffled the first zeroed coefficient across all the other polynomials so that they are spread in all the other polynomials like we have in L-1 other polynomials. So we assume that we generate m signatures, and for each signature, we have a couple of zeroed coefficients, as you see here. Let's say that we were able only to fault 2, and if we shuffle, we will have them somewhere, and we don't know. So the attacker is confused, doesn't know which one to pick in order to apply the attack of SP tau. So that's why we will try to solve this, and we will call the red equations as the correct one and the other one as the incorrect one. And for that, to differentiate between those equations, we will come with 2 conditions. The first one, we took it from the Dilithium specification, so we know that CS1 is always less than beta. And if we know that the y is equal to 0, then with very high probability, we will have the z, or CS1 plus y, is still less than beta. We use this condition to filter, but we can use another one to like more tight condition, and maybe at the expense of more faulted signature. So here we will, if you remember in the description of Dilithium, I said that C is a challenge, which is one polynomial of 256 coefficients where we have exactly tau elements non-zero. So here we can consider that each coefficient of CS1 can be modeled as a sum of tau random variables uniformly distributed over minus eta eta. So minus eta eta is the interval in which we sample the S1, the secret key. So this will give us this bell curve. So the distribution of CS1 will look like this. And we can say that with very high probability, most of the coefficients will be in a certain interval. And we created, using the central limit theorem, this range that CS1 will be always less than 2 sigma. And then in case the y is equal to 0, then this condition will hold. Of course, we are not filtering 100%. There are some false positive into our equation of system, but this will be tolerated by the integer linear program that we would like to use. So we formulate ILP that searches for a secret key S1 such that we maximize the number of fulfilled equations. So here we have 4 constraints. The gamma 1 minus 2 beta is exactly the biggest or the biggest distance between Z and CS. It's in the specification. We didn't come up with some new variables. And we would like to maximize the X. So the X is binary, it can be 0 or 1. If it is 0, then the equation is not fulfilled. And if it is 1, then the equation is fulfilled, and we will look for the secret key S, which should fulfill the fourth constraint. The S should be between minus eta, eta. So the ILP solved efficiently this in practice, and we thought about implementing it. So we had our experimental setup, which is composed of a chip whisperer and a target board STM32F4. We mounted this attack on Dilithium having security level 2. And we worked with a chip whisperer that generates a base clock of frequency set to 7.3. And we had, we worked with clock glitch to mount the attack. So maybe in reality, we don't all have the same conditions or real world, let's say, conditions. So that's why we thought about many questions, like how this attack escalates with a NIST security level, how many coefficients should be faulted per signature, and how many signatures do we need, and especially how much time this ILP takes. So we did a simulation of our attack for different security levels, and as you see here, it shows that the attacks still work for different security levels. For example, if you have little zeroed coefficients, you will probably need more signature. And the more you have, the less signature or the less faulted signature you will need. Maybe this table can explain this better. So if you see the first line, we were able to skip 4 coefficients, and then we needed to get the secret key, 225 signatures. Of course, we had to try to sign many times. That's why the number of executed signatures is 3,600 almost, and 3,400 were like just wrong attempt. And in the best case, in the last line, we have the situation where we were able to fault 252 coefficients. And for that, we needed only 5 signatures to get the secret key. We needed to try with 53 signatures, where 48 were wrong ones, but at the end, we were able to get or to run the ILP in less than 1 minute for all the possibilities. So that was the work for today. Actually, we used integer linear programming in order to get the secret key, and that was not the first time. So we had another attack on Dilithium, which was submitted and accepted at the SAC last year. And we used also ILP there together with profiling side channel analysis. Defending against a fault injection attack of today is not really obvious, especially if you want or if you care about the time, execution, memory, etc. So we thought for the moment about 2 directions: the software countermeasures and also the hardware countermeasures, but we are not, we did not build like a good design yet. For future work, we would like to investigate also the performance of ILP, because till the moment we don't know to which extent it can accept false equations inside it. And we would like also to improve the performance, its performance, maybe to minimize to minimize the number of false equations. And we are also, as I said, looking into improving the countermeasures and making efficient ones. So thank you very much for your attention, and I will be happy to take the questions.
Okay, thank you. No questions? Any question? Yeah.
I've seen another paper that had a look at the loop abort fault, and they found with experiments that when you do the loop abort fault, it may happen, or it happens very often, that it's not actually 0 that's then in the buffer. Did you experience something similar?
Yeah, actually, if you do the loop abort and it is not 0, that means your commitment vector is initialized to some random values. So in that case, if you are using, or if you are always initializing with the same random value, then you will end up with this attack at the end, because if you use, but of course you will use 2 successive signatures and they should fault probably at the same place if you're doing the shuffling in the same way. Yeah, maybe, but I have to look into that. But that was one of the countermeasures, but we would prefer if we can initialize the commitment vector randomly, but in a non-deterministic way. Then in that way, we can avoid with a very high confidence this kind of attacks.
Thank you.
Okay. Another one. Seems no question on the chat. Okay, thank you very much. And now it's time for the coffee break. A long one.